Right, so we've got a further maths vectors problem here. This is to find the equation of a line. This is it's quite involved, this one. This is a sort of I think this is the last question on the paper, and on a core pure paper, which happens to be an Edexcel from the specimen set of papers. So look at the question first. Line L1 has equation that, and the plane 2, has equation that. Right, so and in this we got the diagram here. This is courtesy of Exam Solutions. That's where I've kind of stolen this from, and in fact there is also a very good video describing how you do this kind of problem on Exam Solutions. So I suggest you go and watch, after you've watched this, go and watch that one, and that will really help you understand. Right, so line 1 is this blue line here. The plane is black. And the line L2 is the reflection of L1 in the plane. So that's the blue line. So the L1 is the purple line, L2 is the blue line. So we've got to find that equation of that blue line. Right. So in order to do this, yeah, how can we need, if we find the equation of this line, if we've got 2 points on it, all right? And these are the 2 points that we're going to find. Well, this one here is the intersection of the line and the plane, so that's relatively straightforward. This one is the reflection of well, this point. I mean, it could be any point on the line. But in order to do that, we need to find the equation of this perpendicular. Right. Well, we can find the direction of the perpendicular quite easily, because that's a sort of a standard solution from the equation of the plane. And if we have this purple line in parametric form, it's in Cartesian form at the moment here, but if we have it in parametric form, then we can use the sort of the base point in that form there. All right. So in terms of a plan, what we're going to do here, we're going to first of all find the parametric form of the purple line, the L1. We're going to find the vector of this direction vector here. We're going to find this point here just by banging together L1 on the plane. We can do that. We're going to find therefore we're going to find the equation of this. Once we've got the direction vector, we're going to pick a point on there, and that will give us that quite easily in parametric form. We can then find this point here, the intersection of the perpendicular and the plane. Now that is going to that point is specified, if you like, by the value of the parameter in the equation of this vertical line. And so therefore, if we double that parameter, we'll get this point here on the green line. All right, well, that green line doubles up with a point on the blue line, so that is our second point on the blue line. Okay, so we've got those 2 points then. Right, okay. So that's the plan. So first of all, we're going to convert L1 into parametric form. So this is a standard process. We've got our Cartesian form here. So if you just let this parameter equal all these things, then we multiply out the x, the y, the z, and we can see from that, therefore, that we can rewrite that as in this vector form here. Yeah, 2 plus 40 for minus 2t and minus 6 plus t now. Okay, and that's given us that direction vector for minus 2, 1, which incidentally is these here. The direction vector, of course, could be anything that is some scalar multiple of that. So 8 minus 4, 2 is also specifies a direction vector. We kind of like to put it in its simplest form. That would be the sort of the normal thing. We can also you know, kind of scale it anyway, whichever way we like. So so we got that direction vector, and now we're going to find the normal to the plane. Well, simply, again, standard result, the coefficient of x, y, and z gives us the normal to the plane. So there's there are videos that will actually cover the sort of derivation of that. But it's such a standard result, really. It's just something that you're going to use. Right. Step 3, let's find the intersection of L1 and the plane. Well, we've got L1 in parametric form now. So the question we're asking is for what value of t in this parametric form here satisfies that? Okay, well, we've got all the components, haven't we? We've got the x equals 2 plus 4t. So if that's x, that's the y, that's the z. So if we just substitute those into that equation, we get this. Simplify that to that, and that gives us t equals 2. So the value of t equals 2 in the parametric form of our purple line, L1, then that's what gives us this point here, which is x naught, y naught, z naught in the diagram. Okay, and that works out to be this 10, 0, minus 4. That's that point there. Right, now now the next thing we want is the equation of this perpendicular. Well, yeah, all right, we've got the normal. Well, it's fairly straightforward. I mean, we want a point on this line. The obvious one to take is the one that comes out of this parametric form. We know that when t equals 0, then it passes through that point. So that's the obvious one to take. We could take others, but let's take that one. So therefore, the parametric form of the green line is going to be that same point plus some other scalar times its direction vector. The direction vector coming from there. Right. Okay. Right. That is involved this question because I'm going to have to go out onto another screen. But I've got the diagram down there again. It's just so we want, let's position that correctly. So we want the intersection of the perpendicular and the plane. All right, so that's this point here, this thing. On the diagram they use the parameter t. I'm using s as the parameter for the perpendicular. So in which case, yeah, we got our equation of the perpendicular here. So it's 2 plus s. X is 2 plus s. Y is 4 minus 2s. Z is minus 6 plus s. So if we substitute those into the equation of the plane there, we get this. And that's going to give us s equals 3. Okay. So to get from that point there on the purple line down to the plane, we're doing 3 lots of the direction vector from that starting point. So in order to get down to this point, which is the reflection, now if we do twice as many, in other words, 6 lots of this direction vector, then we're going to get down to this point here, x2, y2, z2. So that's simply this, giving us that point there, 8 minus 8, 0. So that is that one there. Okay, so now if we this point is there, so we have now got two points on the line. So L2 goes through these 2 points here, and so if we want to take the direction vector there, we just subtract one from the other, and that's going to give us that. And if we simplify that, that is going to be 1, 4, minus 2. And no, if we'd actually subtracted them the other way around, then we would have ended up with negatives here. So we can, as well as scaling it, you know, the direction vector, we can also scale it by -1 as well. But that's what we've got. I think the moral of this story is that actually there are, you know, there's lots of different ways of getting to the solution. So we've got our direction vector. We've got a point on the line. I'll use that one. So therefore the equation of the blue line is simply that, plus some scalar multiple. We use r this time for this line, for this blue line, and times the direction vector. So that would be the equation of that line. Right, so that's it basically. One thing I'd say is that there is a formula here for finding the direction vector of the blue line, which takes the direction vector of the purple line by multiplying it out. That's the direction vector of the purple line. That's the normal to the plane there. And these are the dot products. So you could use that. But I always think if you could actually solve these things without using a formula, then somehow that's kind of better. And, you know, if it saves you from having to remember a formula, then, you know, that's it's always good. So hopefully that has been useful. As I say, yeah, you know, have a look at the exam solutions video as well. But I think hopefully that's kind of laid it out sort of quite logically for you, and sort of goes over some of the methods that are used in this kind of problem. So thank you very much for watching.